All right, so we're going to continue where we left off at 8.2. We didn't get to any word problems, so this will be the last thing that we do with law of cosines. And it says that a surveyor wants to find the distance between 2 points on opposite sides of a building. And the surveyor is going to be standing at point C. Okay, they're going to be standing at a third point. So they're looking at points A and B in front of them. There's a house between them. And they want to find the distance between 2 points in front of them from where they're standing. So like the distance along that back wall from my perspective. The surveyor measures two distances from where the surveyor is standing to one point and from where the surveyor is standing to another point. Well, again, whenever you have a word problem, especially like one that's involving trig, the best thing to always do with this is what? Draw it out. So I have a sketch of the whole thing right there. So the surveyor wants to find the distance between 2 points on opposite sides of a building. The surveyor is going to be standing at point C. And then we know a couple different numbers to put into the problem. The distance from point C to point A is 110. The distance from point A to point B is 160. And they also tell us, they don't give it to us in the word problem, they would have to also give us the angle. I don't think that's mentioned. So I'll just add that in. Angle ACB is 54 degrees.
Does it tell you that in like the diagram, but it doesn't say?
Yeah, I just didn't say it in the word problem, so without that you can't. You couldn't do that. So first thing, let's determine like what kind of triangle this is, using the three letters like side, 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 or whatnot.
Side angle side.
Yeah, it's definitely side angle side. And side angle side falls under law of sines or law of cosines. Yeah, it's definitely law of cosines. And this time, they've used capital letters to label the angles. We normally use English letters to label the sides. So I'm not even going to think about this problem really in terms of A's, B's, and C's, because I'm going to confuse it with their A, B's, and C's. I'm just going to think of the idea of the formula. Let's call this side up here X. And that's the distance I want to find. So how would the pattern start out if I want to solve for X?
We do C squared, well, X squared.
X squared, yep.
Equals 110 squared plus 160 squared.
Yep.
Minus 2 times 110 times 160 times cosine of X. 54.
50. There you go.
Yay.
So one side squared equals the sum of the other two minus twice the other two times the cosine of the angle that's across from the side you started with. And we'll just have to use our calculator because we'll get some pretty big numbers. So we've got 110 squared plus 160 squared, 37,700. Minus 2 times 110. I'm going to do that whole thing. 2, 110, 160, cosine 54. 20,690.041. What was it? 041? 041. And what would be my last step? After I can subtract those two, but I'm gonna do that in the last step as well.
Find the square root.
Yeah, find the square root of 37,700 minus 20690.041. So the distance between the 2 points on either side of the building is 130.422. And that is feet. And that's it. They didn't ask you to find any of the other angles or anything, just the distance between points A and B. Any questions on that? So again, with this kind of thing, you don't have to worry about the second answer or the no solution ever happening, because first of all, it's a word problem, and then second of all, it's law of cosines. So if you have a side angle side triangle, you always have a solution. You never have a no solution, and you never have two. You always have one. And that's it. Questions on that? Okay, so another thing that we're going to take a look at is area of a triangle. Now, I've put up the formula that we're used to from geometry, and that formula is fine as long as you know the base and you know the height. But what if we don't know the base and the height? Well, there's two different formulas you can use to find the area of a triangle if you don't know the base and the height. One of them is based off of the law of cosines. That's how it connects with this section. The other one is not. But since they're both about area of a triangle and one of them connects to this formula, usually you do both of them at the same time. All right, let's take a look at this diagram. Now, let's say I wanted to find the area of that triangle, but I didn't know the height. Let's say this is what they gave me. And they'd have to tell me, maybe they'd give me a couple sides and an angle, kind of like side angle side. That's how this formula is going to work. You're going to know two sides and an angle. But not the height. So what you would have to do is figure that height out. Let's see if we could come up with a formula to find the height. And let's use this angle. You could do it from this side, but let's do it from this side. What position is H relative to alpha? Opposite. And how about C? Hypotenuse. And what trig function has opposite and hypotenuse? Sine. So the sine of alpha would equal what? H over C. And what would H equal?
C sine alpha.
C sine alpha.
Yeah.
So that's a formula to find the height if you don't know it. I'll take that, fill it in right there, and now you have a new formula for the area of a triangle that's going to use the sine function. So it's going to be area equals 1/2. What did we call the base in this picture? B. 1/2 the base times the height. C sine alpha. And there you go. 1/2 BC sine alpha. That's one version of the area, but you can write the version using any angle you want, alpha, beta, or gamma. That's the version we just came up with, 1/2 BC sine alpha. Now, look at your triangle. This is A, this is B, C, alpha, beta, and gamma. Does anybody think, if you look at this one, and look at the placement of the B, the C, and the alpha in the diagram, does anybody think they could tell me the version for the area that has sine beta in it? Yep.
1/2 AC.
Yep. 1/2 AC sine beta. And how about the version with gamma?
1/2 AB. Yeah.
1/2 AB. So again, the point here, kind of like the law of cosines, is not to memorize every single possible way you can write it, because then we could do x's and y's and z's and have even more versions. It's the pattern. And the pattern is 1/2 the product of two sides, any two sides you want, times the sine of the angle that is between those sides. That's the pattern. So 1/2 the product of any two sides times the sine of the angle between those sides. So for this formula, it applies to a side angle side triangle. That's where you use this. Let's try it on that one. So the key is, as long as you know two sides and the angle between them, you can find the area. So using that concept, can somebody tell me what the formula would be for the area applied to those numbers?
Times 3 times 12 sine 1.
Yep, sine 105. Yep. And what you're really doing there is you're calculating the height. You just found this. You found the height of the triangle. It's just that calculation for finding the height using sine as opposite over hypotenuse is built into the formula. But that's what you really are doing. 1/2 the base, and then 3 sine 105 is the height. It's one, you're really doing 1/2 base times height. Okay, let's do that. What's half of 3 times 12?
36 would be 18.
So 18. And for that step, we'll need a calculator. So 18 sine 105. So the area is about 17 point, we'll just say 39. We'll just round it to 2. 17.39. And remember, it's an area, so how should it be labeled?
Units.
Whatever unit you happen to have, yeah. Square units. Okay, so 17.39 square units. Any question on finding the area? That's it for that formula. Okay, 1/2 the product of the two sides times the sine of the angle between them. Now, don't write this down yet because I'm going to show you how to do it. What's different about this problem? You don't have an angle. So if I drew this and I said, okay, this side is 9, this side is 7, this side is 5. To find the area, how many angles do you need in that picture?
At least one.
No, just one. Doesn't matter which one you find. You could find any one you want. And this is a side, side, side. So how could you get one of the angles here? What would you have to use?
Well,
Yes. So technically, to find the area of a triangle where you know all the sides, you could just use law of cosines, find one of the angles, and then use the formula I just taught you. But now that's two steps. First, you got to find something that they didn't even ask for. Then you can plug it into the formula we know. Well, there's another formula to find the area of a triangle without having to find this angle. And that's called Heron's formula. Okay, so I'll give you guys a second to copy that. So Heron's formula relies on knowing the three sides. That's what the A, B, and the C are. But it also relies on one more thing, and that's S. If you look at how S is being calculated, can anybody tell me what that really represents? It represents half the perimeter, or the semi-perimeter. Now, the proof of this formula comes from law of cosines. That would be the connection with what we just did. We're not going to go through the proof. This formula automatically finds the angle for you. It's kind of hidden in the formula the way it does it, and figures out the area of the triangle. Right? So let's try finding the area of a triangle where we know all three sides. So the idea is it's the semi-perimeter times the semi-perimeter minus every side multiplied together. And then you take the square root. Okay. So let's add these up. 9 plus 7 gives me, and 16 plus 5, what is it? 21. So my semi-perimeter, let's just write that as a decimal. 10.5. That's all we have to calculate for variables to use the formula. Okay, what comes first in the formula? 10.5 times, and what are we going to put next?
10.5 minus 9.
So 10.5 minus 9, which gives me 1.5. What's going to go next?
3.5.
Yep, 10.5 minus 7, that's 3.5. And Layla, what's going to go last? How did you calculate that? It's S minus every side. One at a time. Oh, Ian, do you know what goes last? 5.5. So we did S minus A. We got that. We did S minus B. We got that. And now the last one we need to do is S minus C. And that gives us the last one. So 10.5 minus 5 is 5.5. And this is a lot faster than using the formula that I gave you at the beginning with law of cosines and then getting the answer. Okay, this generally is faster. Because we're going to type that all in one step and be done. So square root of 10.5 times 1.5 times 3.5. Yeah, do it all at once time.
I wrote
17.412. Well, we'll just say 41. And usually what I do if I have a little bit extra time is I do this problem with law of cosines, find one of the angles, show you using the formula I taught you first, and then do it this way and show you the answer comes out the same. But again, we're not going to go through law of cosines because this formula is faster. Any question on that? I know, again, maybe not as intuitive because I didn't really prove where this formula is coming from, like I proved that one, because that one's very, very quick. The proof of this one, it takes a little bit longer to get through. Okay, probably like 10 or 15 minutes. So for us, it's just not worth it. And you don't even need, I mean, if you don't remember this formula at all, you're going to be fine. You can just use the one that I taught you and actually prove it. It's longer, but it will work. Okay, any questions on that? Okay. So 8.1 and 8.2 were connected because they were both about solving triangles and finding the sides, finding the angles, or finding the area, like we just did. 8.3 and 8.4 are also connected, but they're completely separate from 8.1 and 8.2. So that was the first half of the week. This is the second half. So we know how to write complex numbers like that. Okay, this is something we've talked about before. And does anybody remember like what that form is called? That's not the trig form. That's called something.
Complex?
Yes, what form is that complex number in? Standard. Yep, that's called standard form.
Oh.
Standard form is where you put your real part first, and then your imaginary part with an I next to it. Well, there's another way to write trig numbers, or not, I'm sorry, another way to write complex numbers in what's called trig form.
How do you pronounce that? The larger word is it like trigonometric? Trigonometric. So in trig form, we can do certain things a lot faster than standard form. Think about standard form. If I wanted you to do this out, you're going to have to FOIL. You're going to have to multiply 3 times 8, 3 times 4i, 8 times 6i, combine like terms. Then you're going to get an I squared, which you got to remember is -1. There's a lot of steps to it. But if we can say, all right, we're not going to use standard form anymore. We're going to write it a little differently. We can do a problem like this in like 2 to 3 seconds. It makes it a lot easier to do multiplication and division. Addition and subtraction are already pretty easy. Because if you're just going to add those together, well, that's pretty easy. 3 plus 8 and then 6 plus 4. You're done. But multiplication and division was always kind of cumbersome in standard form. It's doable, but there's a much better way. And that's called trig form. So to figure out what trig form is, the first thing we have to do is kind of visualize complex numbers on a graph. That's going to be the first thing I look at. It's not very hard to visualize complex numbers on a graph. It's going to look basically just like an XY axis, except we're not going to call the axes X and Y. The way that you would represent this on what's going to be called the complex plane is exactly like graphing the number a comma b. So if you wanted to represent 3 plus 6i, if you know how to graph 3 comma 6, that's exactly what this is going to look like. It's going to be 3 to the right, and it's going to be 6 up. But we can't call the axes X and Y. We need an axis that allows us to move in the positive and negatives for reals, and positive and negative for imaginary. The real axis is going to be our horizontal. The imaginary is going to be vertical. And I'm going to go through a couple examples of graphing complex numbers right now, and that's going to connect eventually to how to write a number in trig form. But writing a number in trig form involves visualizing a distance and an angle. And the easiest way to do that is to know where to put a complex number on the graph. Then you can see the distance and you can measure the angle. Okay, so just remember, this is real, that's imaginary. Okay, looking at my first example, what's the real part of that number? So that's going to be 4 to the left. And what's the imaginary part? Negative 2. So 4 to the left, down 2. And that's all there is to graphing, negative 4. Yep, that's it. Now, in a little bit, we're going to be measuring a distance, and we're going to be measuring an angle, and that's how we get the trig form. For now, we're just going to graph. What's my real part here? Imaginary? Positive 3. So negative 2, up 3. There you go. What's my real here? There isn't one. So we're not going to go left and right at all. What's my imaginary? So up 5. And if you're guessing maybe that would have something to do with a 90-degree angle when you write it in trig form, that would be correct. 90 degrees is involved when you would write this number, and also 5 would be involved because that's the distance to the origin. So it would have a 5 and a 90 degrees in it. I'll show you how. How about 6? What's the real part?
6.
And the imaginary? None. So if you were going to be writing that in trig form, instead of writing it as like 6 plus 0i, it would involve a 0-degree angle, and it would involve the distance to the origin is a 6. When the point is on an axis, the distance to the origin, which is something we need to find eventually, is very easy. You just count. But when it's on an angle, we have to talk about how you would figure that out. You might already have an idea how to figure it out. But think about in 1D. What do we call the distance from a number? We don't call it the origin in 1D. We call it 0. What do you call the distance that a number is from 0? It's called the absolute value. Well, this is the distance that the number is from the origin. So if you can find the absolute value of this number, it will give you that length. That's what absolute value is two-dimensionally. It's not the distance from 0, it's the distance from the origin.
Can we just do that in calculation?
Yeah, you might need a calculator for some purpose. But the idea is you're really just going to end up making a triangle. So if this represents a complex number out here, the distance from that point to the origin is called the absolute value. And since it's a distance, it's always going to be what kind of number? Positive. It's always going to be positive. And if you make a triangle out of it, think of the distance as a hypotenuse. Draw a vertical and a horizontal. The real and the imaginary part tell you the length of the base of the triangle. That's the real. And the imaginary tells you the height of the triangle. Once you know the base and the height, how could you find the hypotenuse? Yeah, you just use Pythagorean theorem. We're not using x's and y's, we're using a's and b's. Those are the letters I used to write a complex number in standard form. But it's the real part squared plus the imaginary part squared, and then to add them up and take the square root. So it's really just the Pythagorean theorem. Remember, there is no I that's part of this. A and the B just represent lengths of a side in a triangle. The I just tells you that you were on the vertical axis. So once you mark that point, you're done with the I. And the other thing, kind of jumping ahead a little bit, the other thing we need to find is that angle right there. That's the last piece we need to write something in trig form. And you can probably guess maybe using inverse trig and knowing what those two sides are, the positions of them, how you would get that angle. But it is a right. Well, it's a right triangle, so we don't need to use law of sines or cosines. We can use inverse sine, cosine, or tangent. It's one of those three. Okay, let's try to find the absolute value of that. So if you want to visualize what you're doing, there's the point 3 plus 4i. You're finding that distance. And you're going to think of it as a triangle, just like that. So anyone think they could tell me how I get that distance?
The square root of 9 plus 16.
Yep.
So just use like us.
3, that's 4. And the distance is how much? 5. So that is the absolute value of 3 plus 4i. It's the distance from this point to the origin. 5 units. Any question on that? So that's pretty straightforward. So that last piece that we need is this angle. You might be like, well, why do we need that angle? Well, I'm going to show you why we need that angle. And also to make this maybe connect a little bit more with graphing, I'm not going to use A and B anymore to represent my complex number. I'm going to switch to using an X and a Y. Just because I think if I use X and Y, you'll think of X as horizontal and you'll think of Y as vertical. You can use it, but I think X and Y will make more sense. So let's suppose that we had a complex number written in standard form. And I know normally we put the I after the Y. It's commutative, so it doesn't really matter where you put it. In standard form, you want it at the end. But for what I'm doing, I'm trying to make the formula match with what's going to be in your book. So I'm going to put the I before the Y. X represents the real, Y represents the imaginary. Now, to write this in trig form, you cannot have an X and a Y. You need to get rid of them. Trig form is going to use, well, think what we use in trig all the time. We use angles. So it's going to use an angle. So we're going to have to change X and Y to something. Here's a representation of a complex number. Where X and Y are the real and imaginary. This angle, we're just going to call theta. And the hypotenuse here, I mean, you could call it C, or you could call it H for hypotenuse. But a lot of times, they think of this complex number like that. They think of it as a point on the edge of a circle. So this dotted line that's the hypotenuse would really be like a what in that circle?
The radius.
It would really be like the radius. So they call that side R. You don't have to think of it as being on a circle. I'm just trying to explain to you where the R is coming from. It's not a random letter. It's coming from visualizing the problem that way. Right. Now, let's see if we can write a formula for X. I want to get rid of that X. And I want to rewrite it in terms of other things in this diagram. In terms of this and that. What position is X? It's adjacent. And what position is R in? Hypotenuse. What trig function has adjacent and hypotenuse in it? Cosine. So the cosine of theta would equal what? X over R. Now, I want this X. R times cosine theta. So we just came up with a formula for X that gets rid of it. It's going to use an angle, and it's going to use the distance to the origin, which is the absolute value. This is going to go right there. That's X. Now let's do the same thing for Y. I want to somehow come up with an equation using trig that's going to get rid of my Y. What position is Y in? So now, what trig function involves opposite hypotenuse?
But why do you want to use hypotenuse?
Because it's going to be the absolute value of my point, and it's something I can figure out. I don't want to. That's the only other side that I could use, and we'll be able to calculate it. So what's the opposite? And the hypotenuse. And what about a formula that allows me to replace Y? R sine theta. So that is going to go there. And when you make those two substitutions for X and Y, you have the trig form of a complex number. It's just rewriting the X and the Y in terms of other information in the triangle with trig. So instead of X plus IY, put that for X, put that for Y, and that's how you get what I wrote right there. R cosine theta plus IR sine theta. But what do both of those have in common for factors? They both have an R, and when two things have the same factor in common, what can you do?
Or add them together. Cancel, or either combine them or eliminate.
Well, you can't eliminate it, but you can factor out the common factor.
Yeah, that's what I meant.
So the common factor is R. So the way that you really write a complex number in trig form is R cosine theta plus I sine theta. But in order to be able to use the trig form of a complex number, you need to be able to find the R, and you need to be able to find the theta. You need to figure those two things out. Well, R is just the distance from the origin, which, what did we call that earlier?
The
Absolute value. So R, you just have to find the absolute value, use Pythagorean theorem to get R. Theta is the angle with the x-axis. So what do I mean by that? Let's say there's your line. Theta is right there. It's the angle between the x-axis and your line. Now, let's say your line was over in quadrant 2. Okay, that's fine. Still the same thing. It's the angle between your line and the positive x-axis. That's theta. So it doesn't matter where you put that side, that terminal. You can think of it as like a terminal side. You just have to find that angle. So what we might end up doing is if it's in quadrant 2, what I might do first is figure out that angle, and then subtract it from 180. Or if it was in quadrant 3, I might figure out that angle and then do what with it? Add 180. So we've done that kind of thing before. Okay, we'll think of this as like a reference angle and then add or subtract 180, or if it's in quadrant 4, we would deal with subtracting from 360. But quadrant 1 is the easiest to deal with. Okay, any question on that? So we're going to practice converting a few numbers from standard form to trig form. Okay, we already went through that. So to find r, you're going to use Pythagorean theorem. And I told you to find theta, you'd have to use inverse trig. What I didn't tell you is which inverse trig function. We should kind of think about that now. X and Y are in what two positions relative to theta?
X and Y, they're opposite.
And what trig function would you, like if you set up a trig function involving those two, what would you put? Tangent. And now if you wanted to solve for theta, which trig function would you use to get rid of tangent?
Inverse tangent.
Inverse tangent. So if you're in quadrants 1 or 4, here or here, inverse tangent will work fine. It'll give you the answer because the inverse tangent is always an answer between negative 90 and positive 90. That's the range of inverse tangent. But the problem with that is negative 90 to 90 only covers quadrants 1 and 4. If you have an answer in quadrants 2 or 3, that's the other half of this diagram.
Would it be inverse cotangent then? Would it be something cotangent?
So what would you do to an angle to adjust it so that it's on the other half of the diagram and not this half? Think about if you were on like a circle and you wanted to move to the other half. How much would you have to move? How much? You'd have to move 180. So if you want to get an answer on the other half for quadrants 2 and 3, you still can do the inverse tangent of y over x, but you need to add 180. So to find r, it's Pythagorean theorem all the time. You don't have to worry about anything special depending on the quadrant. But to find theta, you're either going to just do inverse tangent of y over x, or 180 plus inverse tangent y over x. That would be for degrees. Now, if a point is on the axis, you can't really do inverse tangent y over x, because think about like this point. What's the x value of that coordinate? 0. And the y value? Well, we don't know what it is. It's something. Could be 1, it could be 20. But it's 0 comma something. And what would happen if you try to plug in those values into the inverse tangent y over x?
It doesn't work.
You just
It would be undefined.
Yeah, you get an undefined answer because you can't put in 0 for x.
Oh, 0 is X. I was thinking of putting it in for that.
So if you're on an axis, you just need to remember that the angle is either one of these 4 numbers. What are the 4 numbers it could be?
0,
0.
180.
Yeah.
Or 90, 180.
Right. So to figure out
Yep.
your angle, you don't use any special formula if you're on an axis. Okay? It's always going to be one of those 4 answers. So remember, the whole goal is to figure out something that looks like this. We're going to try to write an answer that looks just like that. R, Pythagorean theorem. Theta, well, depends on which quadrant you're in. And an example of a final answer would be this. I'm just making these numbers up. That is a final answer to a problem. That's what a complex number looks like in trig form. You have an R and you have a theta. And you leave it just like that. You don't do this out. If you did this out, what you'd be doing is you'd be changing it back to what you started with. Okay, so we'll go through one right now.
Oh wait, alright, so you're just making those numbers up for the example.
Yep. So now here's some real numbers. I want to find the trig form of -2 plus 2i. What are the two things that I need to find to write something in trig form? I need
R and theta.
R and theta. Okay, I'll do them in that order. R and theta. Let's start with R. Left 2, up 2. That's your R. So using Pythagorean theorem, R is going to end up being the square root of what?
4 plus 4.
4 plus 4. 2 squared plus 2 squared, and then take the square root. So that's the square root of 8, which reduces to
2.82.
reduce, not round.
Sorry, what's next up?
Just reducing the square root of 8.
Oh, that's the square root of 3, isn't it? 2 root 2.
2 root 2.
Yeah, that's what I'm.
Okay, so there's your radius. What's the other thing that we need to find?
Theta.
Theta. And what quadrant is this point in? 2. What did we say on the other page? The formula is to find the angle in quadrant 2.
Theta equals I plus inverse tangent y over x.
Okay, I'm going to do degrees just for this one. It doesn't matter, but I'll do degrees. So 180 plus inverse tangent of, what was my y value?
Wait, sorry, we forget the 180.
That's in the formula.
Oh,
Comes from the formula on the other page. Yeah, so what's my y value here?
2.
My y value is 2. Divided by my x value, -2. So that's really just the inverse tangent of -1, which is -45. So the question is, what is the angle from here to there? $135. Now you take those two numbers and you write your final answer and make sure you put it in that format. Just fill the R in, fill the theta in, and then stop. Don't do anything else. So the final answer is going to be R cosine 135 plus I sine 135. If you said, well, what happens if I take this 2 root 2 and distribute it out? Well, then what you'd be doing is changing it back to what you started with. I can show you. Take 2 square root of 2 and multiply it by the cosine of 135 and watch what you get. -2, which is what you started. So you can check your answer that way. If you want to multiply it back out with distributive property, you'll get back what you started with. But that's how we want to leave it because they said to leave it in trig form. So that's trig.
Sorry, why does it switch from cosine to sine?
Because that's what the formula is when we went through it. The reason why is all this basically right there. Has to do with right triangles. Let's just do another one of those. Find the trig form. Let's do 3 plus 4i. Okay, you don't really need to draw it if you don't want to. There's really not a lot to draw. As long as you can visualize what quadrant this is in, that's what you need to know. Okay, so what quadrant are we in? We're in the first. What's the formula to find your angle in the first quadrant? What's your formula to find theta in the first quadrant?
Inverse tangent, root
Inverse tangent,
4
y over x. And because we're in the first quadrant, I should have mentioned it, but do we need to add 180? No, not in the first quadrant, not in the fourth quadrant. So inverse tangent of 4/3 gives me 53.13. So there's my angle. What's the other thing I need besides my angle?
R.
I need my r, so that's the distance from that point to the origin. And how do we get r? Yeah?
Square root of 9 plus 16.
Yep, it's the square root of x squared plus y squared, which is going to give me 5. Okay, so I have the 2 pieces of information I need. Now I just write my final answer. What is my final answer going to look like in trig form?
Cosine 53.13.
Yep, so don't forget your parentheses.
Oh, yes.
And you leave it just like that. If you want to check your answer, you could multiply 5 times cosine 53. And you should get back what you started with. How come I didn't quite get back 3?
Because you rounded it to 0.13.
Because I rounded it, but I mean it's close enough that I know it's correct. Okay, so that's how you change a number from trig form or to trig form. What if I had, let's just say you had something like this, and I said to you, change that to standard form. What would you do with it? Yeah, just distribute it out. 2 cosine 10. So it's like 1.97. And what would you type in for the imaginary part?
2 sine 10.
2 sine 10. Point
Why is that 2 sine 10?
347.
Oh, because it's.
It's a lot easier to change something back to standard form because all you have to do is distribute. It's harder to change it to trig form because you got to find the radius and you got to find the angle. But you can convert both ways. Okay, so the last thing we're going to look at tomorrow is what what's the advantage of writing a number in trig form? Well, it gives us a very quick way to multiply and divide. So we were almost done. So multiplying and dividing. And then 8.4 is still looking at numbers in trig form, but taking square roots and raising to powers. So there's 4 things that we're going to look at how to do with these numbers.
Alright, that's not gonna work for tonight, is it?
No. Homework for tonight.
Yeah, I don't want to do anything about